Hello students, today we will discuss the Kruskal algorithm. Kruskal algorithm is generally used to find minimum spanning tree from a graph. So first we will discuss what is spanning tree. So let's suppose one graph which is a connected and directed graph where V denotes a set of vertices and E denotes a set of edges. Now each edge here has non-negative length, cost or weight. Now problem is to find a subset T of the edges G such that all the vertices remain connected when only the edges in T are used. The sum of the cost of the edges in T is as small as possible. The cost of a tree T is denoted by CT is the sum of the cost of the edges in the T. Now minimum spanning tree or the MST of G is a spanning tree T star of G with the minimum cost. So whatever edges we have included in T, it should result in the minimum summation and all the vertices would be covered for this spanning tree. So minimum spanning tree is the spanning tree uh, where the summation of all the edges included in the minimum spanning tree would result in minimum sum. Now let's take one example. Suppose we have been given here this graph with this A, B, C, D, E, F vertices and edges are given with some weight. Now how the Kruskal algorithm works. So the first step is we have to arrange all the edges in the ascending order of its weight. So here is the table where we have written all the edges in ascending order. Now we have to take the first edge and add into the minimum spanning tree. So the first edge is CF and its weight is equal to 1. So we will add that edge in the minimum spanning tree. The next edge is AF which has the weight 2. So we will add that edge. Next edge is DE which has the weight 2. So we will add that edge also. Now CD we will add that edge also with the 3 weight. Now the next turn is of the EF edge. So if we add EF edge then it will result in a cycle. Closed loop will be formatted. So that EF edge will not be added in the minimum spanning tree. So now the next turn is of the AB edge with the 4 weight. So we will add that edge into the spanning tree. Then after the next turn is of the BF which has the weight 5. So if we add this BF edge then you can see that it will result in a loop or the cycle. So we cannot add that edge. The next turn is of the BC edge with the 6 weight. So if we add that edge then again the cycle will be formed. So BCH cannot be added to the minimum spanning tree. So by looking at this resultant tree you can see that all the vertices of the original graph are in the minimum spanning tree with the edges with least weights. So this is your minimum spanning tree from this for this graph. So the total weight here for the minimum spanning tree is 12. All the vertices are in minimum spanning tree with the least weight edges. Now Kruskal's minimum spanning tree algorithm relies on a disjoint data structure to maintain the components of the intermediate spanning forest. So first we have to understand what is disjoint data structure, what are the operation of this data structure and how it will help in the Kruskal algorithm. Right? So first operation of the disjoint data structure is make set. So make set is used to create a new set for a single element X. So it will create a new set X containing the single element X. Now that object X must not appear in any other set in our collection. And the leader of the new set is obviously X. So this is the make set. If we talk about the graph, then we have to create a set for each and every vertex of a graph. Now find operation will find the leader of the set which contains the X. And the next operation is union where two sets are given A and B. So if we perform the union operation on these two sets A and B, new set will be created and this A and B will be replaced by that new set. So the union operation replace two sets A and B in our collection with their union A union B. Now we will understand the disjoint data structure with an example. here two elements are given A and B. So first we are creating a set for these two elements A and B. So make set A and make set B operations will be called, and new sets S1 and S2 are created which represents A and B. Now if we perform the union operation on these two sets, then it will combine these two elements and S1 and S2 will be replaced by S3. So in this new set S3, A and B will be combined. So now uh, S1 and S2 replaced by S3. Now if we call the find operation of A and B, so now the representative set of A and representative set of B is S3 only, which contains that two elements A and B. So both these find A and find 2 function will return the same set 3. Right? Now if I take another example, then if I call this function union A and make set X, then what it will do, it will create a new set which has A and the X. So it adds a new element X to an existing set of A. Now we'll understand the Kruskal algorithm for finding the minimum spanning tree. So this is the algorithm. Now Kruskal algorithm will take two parameters. First is the graph, which indicates or which gives you the number of vertices and edges, and the weight function will give you the weights of all the edges. Now the first step is the initialization phase, where A is equal to 5 means A is in solution set. Right now there is no edge in the A. So A is equal to empty. Now in the next step, for each vertex V which belongs to the graph, we have to create a set for each vertex. So the second and third step will create a set for each vertex of a graph G. Now in the fourth step, we have to sort the edges of E into non-decreasing order by weight W. So we have been given the weight array. So based on that, we have to arrange all the edges in non-decreasing order. Now in the fifth step, for each edge UV which belongs to the set of edges of graph G taken into non-decreasing order by weight, we have to find out the set of U and V, right? So we will call this condition find set of U and find set of V. If both are from the same set, then that particular edge UV will not be added to the solution set, because it will create a cycle. So if this condition is true, where the set of U and set of V are different, then and only then the particular edge will be added to the solution set. And after adding that edge into the solution set, you have to call the union operation on UV. So these two sets will be combined and another set will be created which stores U and V both. So this 5 to 8 operation would be performed for every edge of the graph, right? And in the last step, we have to return the solution set. Solution set A will store all the edges of a graph, which will create a minimum spanning tree. Now let's solve the previous example that we had seen using the Kruskal algorithm. So here all the 6 vertices are given A, B, C, D, E, F with the weight values for all the edges. The first step of the Kruskal algorithm is to initialize the solution set. So here we are initializing the solution set with 5, means no edge has been added yet to the solution set. In the second step, we have to create a set for every vertex of a graph. So this graph is containing total 6 vertices A, B, C, D, E, F. So we are creating a set for each vertex. Make set A operation will create one set which represents A. Same way, make set B will create a set which represents this object B. So this is how we have created the set for all the vertex of a graph. Now from the fourth step, we have to first arrange the edges into the non-decreasing order. So in the fourth step, we are writing this table where all the edges are written in increasing order. Now, in the fifth step, we have to check the edges of a graph. So first we will take the edge CF with the least weight 1. Now we will find out that the two vertices from which this edge has been created are from which set? So the set of C is C and set of F is F. Both the vertices set are different. So we can add that edge into the solution set. So we will add that edge into the solution set. So now solution set is containing CF. Now after adding the particular edge into the solution set, now we have to call the union operation. So if we call the union operation on this CF, the new set will be created, and in that set both the elements C and F will be added. So new set will be created which represents both C and F. Okay. Now in the second iteration we will take the edge AF with the weight 2. So now again we will check the representative set of A and F. So we have new set from the previous iteration which represents this CF, right? So now the set of A is A and the set of F is this new set. So both the sets are different. So we can add that AF edge into the solution set. And after performing the union of A and F, what happens? These two sets will be merged. So the new set will contain A, C, F, these three elements. So now this AF will be added to the solution set, and by the union operation new set is created which represents this A, C and F. Now in the third iteration we have to take the next stage DE with the weight 2. The same way we can again check the representative elements or representative sets of D and E. So the set of D is D and set of E is E. Both are different. So we have to add that HDE into the solution set, and after performing this adding or in the solution set we have to call the union operation. So new set will be created which merge D and E both. So new set will be created and the representative elements of this set are D and E. So now after this third iteration we have two sets. One set is storing ACF and another set is storing this D and E. Now fourth iteration we will take this CD edge with the 3 weight. Now we will again check the representative elements of C and D. So representative set of C is this new set and representative set of this D is this new set 1. Both are different. So CDH can be added to the solution set. Okay. Now here if we call this union operation on this C and D, what happens? These two sets will be merged and replaced by the new set. So new set will be formed and now this set is containing A, C, D, E, F. All these 5 elements or vertices are added to the new set. Now in the next iteration we will take the EFH, right? So now we from the previous iteration we have this set where, which stores this A, C, D, E, F, right? So now we will check the representative set of E and F. So if we check the condition, then what happens? Set of E is new set of F is also new set, both the sets are same. So that particular edge EF cannot be added to the solution set. Okay, so the solution set will remain same from the previous iteration. Now in the sixth iteration we will take the AB edge, right? So now set of A is new set and set of B is B because it is not in the new set. So representative set of A and B are different. So we can add that edge into the solution set, and when we perform the union operation B will be added to this new set. Okay, so now the solution set is containing these edges and new set will contain A, B, C, D, E, F. Now we'll check the next iteration. In the next iteration, now there is a turn for the BFH. Okay. Now the representative set of these two vertex B and F both are same because both are in the same set. So that particular H cannot be added to the solution set. In the last iteration, BCH will be taken. The representative set of this B and C are same because they are in the same set. So that particular age also cannot be added to the solution set. So the solution set is this, where 5 ages are added. Okay, so you can see that all iterations are completed, and now this is our solution set where 5 ages are added. Now if we take this 5 ages, then the total weight of this minimum spanning tree is 12.